When you get right down to it, down to the very bottom of everything we see, everything we are, what is reality made of? Is the universe this perfectly smooth, continuous fabric, or is it actually kind of grainy, like a pixelated grid? That's the question we're tackling, a deep investigation into what our universe is really like. Okay, here's a good way to think about it. Imagine our reality is like a movie. Is it an old school film reel where no matter how much you magnify it, the image just gets smoother and smoother? Or is it more like your computer screen, where if you zoom in far enough, bam, you hit the individual pixels. You can't go any smaller. Seriously, this is one of the biggest, most fundamental mysteries in all of physics. So this whole mystery really boils down to two possibilities. Two completely different realities. On one side, you've got the continuous idea. This is the world of Einstein's relativity, where space-time is this smooth, stretchy fabric. Then, on the other side, you've got the discrete camp. They say, nope, at some super tiny level, space is actually made of these little indivisible chunks, pixels, if you will. And there is literally nothing in between them. And believe it or not, this isn't some newfangled debate. We're talking ancient Greece here. A philosopher named Zeno was already wrestling with this. He came up with these famous paradoxes, basically asking, hey, how can you ever get from point A to point B if you have to cross an infinite number of halfway points first? It's a real head-scratcher. And his solution? Well, he figured there must be some smallest possible step, a final indivisible piece of distance you can't cut in half. All right, so to get to the bottom of this cosmic mystery, we're going to treat it like a detective story. Here's our plan. First, we'll look at the mystery itself, smooth or pixelated. Then we'll go to the crime scene, the universe's ultimate resolution limit. We'll check out the discrete suspects and then the continuous ones. After that, we'll examine all the forensic evidence and finally try to put together the final cosmic picture. Okay, let's dive in. Our investigation starts at a place called the Planck scale. Think of this as the scene of the crime. This is the wild frontier where our two best theories of the universe, general relativity and quantum mechanics, just stop working. It's at this scale that the universe has to show its true colors. So what are we talking about here? We're talking about the Planck length. Look at that number. To write it out, you'd have a decimal point, then 34 zeros, and then the 1616. It is ridiculously, absurdly small. In fact, a lot of physicists think this is the smallest meaningful distance that can even exist. Anything smaller than this, and the whole idea of space just kind of falls apart. Just to put this into perspective, because it's kind of impossible to imagine, take a single atom. We think of atoms as tiny, right? Well, a single atom is about 100 quintillion times bigger than the Planck length. That scale is it's staggering. It's a world so small it's almost meaningless to us. But that's where the secrets to reality are hiding. And the Planck scale isn't just about distance. It's actually a whole set of fundamental units for time, for mass, for energy. They're sometimes called God's units. And that's because they're not based on anything human, like the length of a king's foot. They're derived from the fundamental constants of the universe itself. They're as natural as it gets. So the obvious question is, why can't we just build a super powerful microscope and take a look? Well, physics has a really cruel catch-22 for us here. See, to look at something really, really small, you have to hit it with a ton of energy. But if you try to probe something as tiny as the Planck length, you need so much energy that its own gravity would instantly cause it to collapse into a tiny black hole. And poof, the very thing you were trying to look at gets swallowed, hidden from you forever. Frustrating, right? Okay, so since we can't look directly, we have to rely on theories. And that brings us to our suspects. First up, let's look at the case for a pixelated reality. These are the theories that say space-time is built out of fundamental atoms. And a major player in this discrete camp is a theory called loop quantum gravity, or LQG. The core idea behind LQG is just wild. It says that space isn't some empty background, some container that stuff exists in. No, it says space itself is built from something, constructed piece by piece from these indivisible little chunks of geometry. So how does this work? Well, in LQG, space is kind of like a network, a web made of nodes and links. These links represent the smallest possible bits of area, and the nodes are the smallest possible bits of volume. The best analogy, really, is that digital photo. If you could zoom in on reality all the way down, you wouldn't get a smooth picture. You'd find the actual fundamental pixels of space-time itself. But hey, what if reality isn't pixelated? That brings us to our other set of suspects. These are the theories that hold on to the idea that space-time is fundamentally smooth and continuous, but that there's a different reason we can't see past a certain limit. Now, the heavyweight champion in this corner is, of course, string theory. You've probably heard of it. It takes a different approach.
It says the most fundamental things in the universe aren't little points or pixels, but tiny, vibrating loops of string. And here's the key part. These strings exist and do their thing inside a spacetime that is perfectly smooth, perfectly continuous.
So this is really the core of the disagreement between our two main suspects. Let's break it down. Loop quantum gravity says space-time itself is quantized. It's chunky. It's made of hard pixels. String theory, on the other hand, says space-time is smooth, but we can't resolve anything smaller than a string because, well, strings are the smallest things we have to look with. It creates a sort of blurry limit instead of a hard pixelated one. Okay, that's enough theory. Any good investigation needs hard evidence. So let's look at the forensics. What have our real-world experiments actually found in this hunt for space-time greeniness? One of the most fascinating experiments was the holometer over at Fermilab. Basically, they used these incredibly precise lasers to see if space-time itself is perfectly still or if it has a tiny jitter to it, a kind of quantum noise that some of these pixelated theories predicted. And the verdict? They found nothing. Zilch. The holometer didn't see any jitter at all, which was a big blow to the simplest grainy models. Scientists have also come up with another really clever test, using light from these massive cosmic explosions called gamma-ray bursts. The logic goes like this. If space-time is grainy, like a bumpy road, then high-energy light, think blue light, might travel just a tiny bit slower than low-energy light, or red light. Over billions of light years, that tiny difference should become noticeable. But guess what? We've looked, and photons of all energies arrive at the exact same time. It's another piece of evidence that puts these simple grainy theories in a really tough spot. And there's even more. People have pointed out that if space-time was this churning, fluctuating quantum foam, then images of really distant galaxies from the Hubble telescope should look blurry. But they don't. They are shockingly, beautifully sharp. It seems like all the forensic evidence is pointing in the same direction, doesn't it?
Okay, we've been to the scene of the crime, we've interrogated the suspects, we've looked at all the forensic evidence. So, what's the verdict? What's the final cosmic picture, at least for now?
And the verdict is, well, it's pretty clear. For now, there is absolutely no smoking gun for a pixelated universe. Every single experiment we've thrown at this problem, every test we've designed to find that graininess, has come up completely empty. As far as we can possibly tell, reality seems to be perfectly, frustratingly smooth. Now, that could mean it really is continuous, or it could mean the graininess is just way more subtle than we ever imagined. But before we close the case file on this one, there is one last truly mind-bending idea we have to talk about. It's called the holographic principle. This is a radical concept that grew out of studying black holes, and it suggests that maybe, just maybe, our entire three-dimensional reality is nothing more than a projection, like a hologram, with all the information that makes up our universe encoded on some distant two-dimensional boundary. Now, just think about what that means. If this holographic idea is right, it changes everything. It means the most fundamental building block of the universe isn't matter, it's not energy, it's not even space itself, it's information. The universe isn't a collection of things, it's a collection of bits. And that leaves us with this final, absolutely wild question. What if this whole debate, smooth versus pixelated, is the wrong way to look at it? If information is what's truly fundamental, what does that say about our reality? Could it be that our entire universe is just one grand cosmic projection? A reality whose ultimate resolution isn't measured in inches or meters, but in bits and bytes?